The advent of modern physics gives rise to a series of quantum numbers that fall out of some of the complex mathematics that's necessary to describe where electrons are likely to be found around the nucleus of an atom. These quantum numbers, of which there are 4 that pertain to electrons, specify an address where we're likely to find an electron. And just like your home address might not necessarily always mean that you are home, an electron's home address doesn't mean that we know an exact location for an electron. It just specifies a place where we're likely to find an electron. Again, there are 4 quantum numbers. Here we're going to talk about 3 of them. And we're going to talk about them in narrower and narrower scope. So the first of these quantum numbers is very broad in scope. We can think about this very first quantum number that we'll discuss as being akin to the state in which you live. You might live in Wyoming, but saying that you live in Wyoming doesn't do a whole lot to narrow down precisely where you might be at this point in time. That first quantum number is called a principal quantum number. The principal quantum number, or lowercase n for short, is to an electron exactly like the shelf on a bookshelf analogy. Here, though, this principal quantum number specifies an energy shell rather than an energy shelf. It's effectively a small cloud in which we can expect to find an electron. As the principal quantum number n increases, this energy shell becomes larger and larger and gets farther and farther away from the atomic nucleus. We can count energy shells just like we counted shelves on a bookshelf. And the values for this principal quantum number can start at 1 and increase in integer form all the way up to infinity. There are hypothetically an infinite number of possible principal quantum numbers, or energy shells, in which an electron can reside. A second quantum number specifies the shape of path that an electron takes as it waves its way through a given energy shell. This is called an orbital angular momentum quantum number. The orbital angular momentum quantum number, abbreviated lowercase italicized L, gives us an idea about the shape of an orbit within a particular shell. In an analogy to the bookshelf like we talked about earlier, think about this quantum number as being like a box of a particular shape and size that can sit on a particular shelf on our energy bookshelf. This is an orbital shape. There are hypothetically an unlimited number of orbital shapes that electrons can take on, but so far, in ground state electron configurations, electrons only adhere to 4 shapes in the elements that we have synthesized or discovered thus far. The shape of an orbital depends upon the energy shell in which that orbital resides. That means that any orbital angular momentum quantum number is restricted to particular values, or quantum numbers, on the basis of the energy shell, or energy shelf, on which it sits. The values for L depend on n. Specifically, the values that L can take on numerically start at 0 and can increase to infinity, but can never be more than n minus 1. The energy shell number -1. For example, on the second energy shell, the value of L could be 0, could be 1, but could not be 2, and could not be anything higher than 2, because on the second energy shell, n minus 1 is 1. To make things all the more confusing for first-year chemistry students, in addition to calling these orbital shapes by their numerical value, we can alternatively and additionally describe them in terms of a letter designator. These orbital angular momentum quantum numbers are better known by their letter designators, in fact, because such letter designators were an archaic form of orbital angular momentum quantum numbers before we even knew what the mathematics that gave rise to these quantum numbers was. These letter designators come from historical descriptions of atomic spectra that can be described as sharp, principal, diffuse, or fine. The alternate letter designators for L is equal to 0 include S, for L is equal to 1, P, for L is equal to 2, D, and F for L is equal to 3, saying either these numerical values for this orbital angular momentum quantum number or these letter designators means precisely the same thing. From now on, we're going to tend to refer to these orbital shapes using these letters, S, P, D, or F, SPDIF. These are the only orbital shapes that are verified to exist, although a hypothetically infinite number of orbital shapes could exist. And for orbitals beyond F, we just label in increasing alphabetical order, G, H, I, etc. Those orbitals have specific shapes. S orbitals, for instance, represent spherical shapes through which electrons can orbit. P orbitals represent peanut or bow tie shapes. D orbitals are daisy-shaped or cloverleaf shaped. F orbitals are freaky and have wacky, out-of-the-box shapes. What we're going to do is sketch the shapes of these orbitals so that we can visualize what each one looks like. An s orbital is a spherical shaped orbital. And remember, we can use a good analogy like boxes on shelves. An s orbital is like a spherically shaped box that sits on the shelf of a bookshelf and can house electrons in it. In three-dimensional space, if we draw an axis with x and y and z coordinates, this just looks like a blob with a center at the origin of these axes. So this might represent an s orbital, and within this s orbital could be housed some electrons. We don't know where within that box those electrons are right now, but what we do know is that they're confined to that box. P orbitals are shaped like a peanut. P orbitals in three-dimensional space, again, where we have an x-axis, a y-axis, and a z-axis, extend outward in two lobes along one axis. There might be a lobe right here, which is mirrored on the opposite side of the x-axis. What's unique about p orbitals and all the orbitals as we move to more and more complex ones is that there are multiple ways in which we can orient these orbitals in space. A p orbital doesn't have to be confined to just residing around the x-axis in 3 dimensions. It could sit around the y-axis, and it would look like this. Or it could sit around the z-axis, and it might look like this. All told, there are 3 possibilities for orientation of p orbitals in space. Therefore, when we consider p orbitals, these peanut-shaped orbitals, moving forward, we're going to keep in mind that there are 3 ways that these orbitals can be oriented, so 3 distinct possibilities for them. Each one of these possible orientations can independently contain electrons. And if you're following that pattern, you might imagine that d orbitals, which have a daisy or cloverleaf shape, have 5 possible ways that we can orient them in space. These are more complex still. So there are 5 possible orientations. I'll try to depict these 5 orientations graphically in a tricky way. What we're going to do is take advantage of how we draw axes and label them on these 5 different graphs. The first I'll draw conventionally, x, y, and z axis coming out of the screen and towards you. The next one that I'm going to draw swaps the z and the y axis. So I'm just going to rotate this plane so that z points up and y comes out of the screen towards you. Next, I'm going to swap x and y so that y is over here and x is going up while z is still coming out of the screen towards you. Next, I'm going to have the same configuration as before. Y over here, x up top, z coming out of the screen towards you. And for the last, we'll have x coming out of the screen towards you, y over to the right, and z up top. These are just different ways that we can orient our Cartesian axes in space to depict differences in how these d orbitals themselves are oriented. The first d orbital possibility lies in a plane between the x and the y axes. It has 4 lobes to it, and it looks like this. For short, we call this the dxy orbital to specify that it sits between the x and y axes. When a similar looking structure sits between the x and the z axes like this, we call the resulting orbital a dxz orbital. A d orbital that sits along the x and the y axis like this is known as a dx squared minus y squared orbital. Notice that this is rotated 45 degrees from the first one that we drew. Next, I'm going to skip down to the bottom right, and we're going to draw an orbital that exists between the y and the z axis. We call this orbital the dyz orbital. And lastly, we'll draw an orbital that looks kind of strange compared to these cloverleaf shapes. This will be called the dz squared orbital, and it looks like this. This is a 2-lobed orbital surrounded in the center by a halo, the dz squared orbital. All told, these are 5 possible orientations of the d orbital, and, like the other orbitals before, each is capable of housing electrons. I'm not going to bother trying to draw f orbitals because they are just too complex for my poor artistic abilities to be able to even attempt. So to recap up to this point, we have discussed 2 quantum numbers. The principal quantum number is an energy shell, like shelves on a bookshelf, numbered 1, 2, 3, and so on. On a given shelf, electrons can reside in certain orbits or fit inside certain shapes. These shapes are described by the orbital angular momentum quantum number, L, that can have values of 0, 1, 2, 3, and so on, but only up to n-1 for a particular energy shell. We're limited by the upper limit of n-1. And what's more is that these orbital shapes have possible orientations that can differ in 3-dimensional space depending on how we orient them. we can describe the nature of these possible orientations through a third quantum number called the magnetic quantum number, or m sub L. M sub L will describe the orientation of orbitals and give us a count of the total number of possibilities that we have for a particular type of orbital. M sub L depends on L. So, what we're doing is developing a hierarchical list where each quantum number in turn gets progressively more narrow in scope, and each quantum number in turn depends on the quantum number that came before it. Values of L depended on values of N. Values of M sub L depend on values of L. Specifically, M sub L can have numerical values that range from negative, whatever L is for a particular orbital shape, through the number 0, all the way up to whatever positive L is. Let's do an example for d orbitals, where the orbital angular momentum quantum number L is equal to 2. For a d orbital, where L is equal to 2, the possible values for M sub L, according to this rule down here, could be -2, and counting in integers through 0 will eventually get to +2. We're going to fill in integers along the way. The integers in between -2 and +2 are -1, 0, and +1. The possible values for M sub L are -2, -1, 0, +1, and +2 any time that the value of L is equal to 2. These numbers in and of themselves don't have a whole lot of meaning to a general chemistry student. What's going to be more important for you is your ability to count how many different possibilities for M sub L there are. Here, in all the quantities that we wrote down for M sub L, we have 1, 2, 3, 4, 5 possibilities, 5 possible values of M sub L in any d orbital. What this means is that there are 5 possible ways for us to orient a d orbital in 3-dimensional space. In fact, anytime we can count up the total number of possibilities for these magnetic quantum number values, we'll get the total number of possibilities for ways in which we can orient orbitals in space. The values of M sub L for a p orbital, for instance, range from -1 to 0 to +1, with 3 distinct possibilities. Therefore, 3 possible orientations of a p orbital in space. All told then, if we go back to our orbital shapes and superimpose all of the possibilities for p and for d orbitals on top of one set of axes, what we find is that s orbitals, spherical orbitals, with only one possibility for orientation in 3-dimensional space, looks fairly benign. P, or peanut-shaped orbitals, these bow tie shapes, can have 3 distinct possibilities. One oriented along the x-axis, which we call px, another along a y-axis, which we call py, and a third along the z-axis, which we call pz. D orbitals get significantly more complicated. These are daisy or cloverleaf shaped orbitals that have 5 distinct possibilities for how they can be represented in 3-dimensional space, and superimposing all 5 possibilities now looks like this giant cluster of stuff. It would be too complex to show all 7 f orbitals on one graph And so here are 7 distinct possibilities for f orbitals. Notice that we form a pattern. There's 1 possibility for s orbital orientations, 3 for p orbitals, 5 for d orbitals, and 7 for f orbitals. As we increase this angular momentum quantum number, we increase the complexity of the orbital shape or box in which electrons may be contained. The caveat to this is that we restrict the availability of certain orbitals on certain energy levels. Remember that a few moments ago we said that L can have numerical values of 0, 1, 2, 3, and so on, but only up to n-1. In other words, the energy shell on which an orbital exists dictates the shapes of orbitals that may reside in that shell. 0, S, 1, P, 2, D, and 3, F. On the first energy shelf, or within the first energy shell, where n is equal to 1, n-1 is 0. Thus, the first energy shell can house shapes of orbitals whose orbital angular momentum quantum number does not exceed 0. Therefore, s orbitals can be found in any energy shell. Where n is greater than or equal to 1. For p orbitals, though, whose orbital angular momentum quantum number is 1, we cannot house a p orbital in the first energy shell. But beginning on the second energy shelf, where n is 2, and 2 minus 1 is 1, we can begin to house p orbitals. P orbitals can be found on every shelf except the first. P orbitals may be found in energy shells 2 and up. Another way to say this is that n is greater than or equal to 2. D orbitals may only be found on energy shells 3 and up, because 3 minus 1 is 2, and D corresponds to an orbital angular momentum quantum number of 2. D orbitals are found in shells 3 and up. Or in other words, n has to be greater than or equal to 3 to house d orbitals. And like you might expect, f orbitals with orbital angular momentum quantum number 3 must be found in shells 4 and up. Or, mathematically, the principal quantum number n for the energy shell must be greater than or equal to 4.